Russ. So in terms of the rest of the day, we've got only a couple things, a couple of technical talks left, and then just some closing remarks by our executive director. And so we're running slightly behind, but if anyone can go fast, it's Greg Hankins who's going to tell us how Ethernet is getting faster and faster, what's new and what's next.
Hi, thanks, Tony. So I've given this presentation in various versions and evolutions for about 10 years, and I used this opening slide before, but I wanted to bring it back because I look at it, and this turns out this diagram was drawn 42 years ago. And I'm always kind of impressed and struck by how much they got right. And now over 40 years later, Ethernet is the predominant networking technology that is in use today, and it continues to evolve. So I think it's kind of cool to show this historical diagram. There's a lot going on with Ethernet. In the past, I've talked about 100 gig and 400 gig, but now there's a couple of different speeds that we've added to the roadmap for different applications. So we'll talk a little bit about market evolution and then what's next and what's new for some of the various different speeds. If you look at the market requirements, we've had fairly linear increases in Ethernet speeds, but now we're seeing different requirements for different applications in terms of speed, distance, cost, some of the legacy constraints, for example. So it turns out that we're doing a lot of different new speeds. We have the potential to do 6 new speeds in the next couple of years, which is the same amount that we've done in the past 30 years. But there are good reasons for that. So it may look a little chaotic. It may look like we're a little bit exuberant over different speeds, but there's good reasons why we're doing these. So for wireless access points, we're looking at 2.5 and 5 gig. For server applications, we're looking at 25 gig. And for core networks, we're looking at doing 400 gig. In terms of the market applications, 10 gig is obviously very widely deployed, so we see 10 gig deployed everywhere. We're working on new applications for 2.5 and 5 gig, again driven primarily by the requirement for higher wireless access points. Also a very large installed base of Cat5 and Cat6. For data center access and server NICs, we're working on 25 gig. We have more interfaces for 40 and 100 gig that I'll tell you about. And then also we're working on 400 gig for core applications, as I mentioned. Let's start looking at the market drivers for 2.5 and 5 gig in particular. We have a number of wireless access point speeds that are now exceeding the wired capacity. So we have, for example, 802.11ac can go up to about 7 gigs, but you only have a gigabit wired link that goes back into the rest of your network. And in the next couple of years, we're going to have 802.11ax, which has the potential to go up to 4 times faster than .11ac. So clearly we need some sort of faster wireless backhaul on the wired side to avoid the bottlenecks. The rule of thumb is that you need about 75% wired speed to avoid the bottlenecks. So clearly that you can see the math works out that we need 2.5 gig and 5 gig that runs over Cat5 and Cat6, and then of course we need PoE as well to power those access points. The other market driver for 2.5 and 5 gig is the very large installed base of Cat5e and Cat6. So we have higher speeds. We have 10G base T that only runs over Cat6a or Cat6. We have 25G base T and 40G base T that we're working on. That requires Cat8 and only goes to 30 meters. So there's a desire to reuse a lot of existing infrastructure for higher speeds. The IEEE references a study that's shown here. I'll just tell you some numbers. Just in 2014, for example, 58 billion meters of Cat5 was sold worldwide. This translates to about 90% of the installed outlets. The very interesting thing is that data centers only make up about 4% of that installed base. So you think about every hotel, conference room, school, apartment building, office building, a gas station, bars, restaurants, wherever. This is all where the Cat5 is being installed, and that's where the large install base is that we want to reuse. Wireless is listed as a primary application, but there's also examples for higher speed desktops, small cell, HD cameras, and all sorts of things that could take advantage of this higher access speed that runs over Cat5e and Cat6. The IEEE has a new task force. It's called 802.3BZ. It was just formed a couple months ago. They had their first meeting 3 weeks ago, so there's not really a whole lot to report yet. They're going to define 3 new speeds, 2.5 gig over 100 meter Cat5, 5 gig over 100 meter Cat 5, and also 5 gig over 100 meter Cat 6. It's going to support some sort of auto negotiation between the different base Ts. So we have 2.5, 5, 10, 25, and 40G base T now. And they're working on the first draft. So again, not a whole lot to report yet. The standard and interfaces should be available sometime on the market in about 2016, sometime next year. There's two industry groups that are also working to define standards and build consensus. There's the MG-based-T Alliance, which was formed by Broadcom based on one of their early specifications. And then there's the N-based-T Alliance, which is basically everyone except Broadcom. So these groups are working to help define the standards and influence the IEEE. Okay, on to 25 gig. This is an interesting one, and we're spending some time on because it's kind of a fundamental change in how we're doing the signaling. The goal of 25 gig E is to provide a server connection speed that's faster than 10 gig, that is also optimized for cost, throughput, and efficiency, and to maximize the efficiency of the servers that are connected to top-of-rack switches and data centers. I have some math that I'll show you on the next slide that explains how this works. But basically, in terms of the Ethernet signaling, the basic building block that we used to use was a 10 gig signal on the electrical and the optical side. That's moving to 25 gig, so it's kind of like 25 is the new 10, and we're using it everywhere already. We're using it for 100 gig, we're using it for Cowie 4, which is the electrical signaling used for 100 gig, and we're using it in a lot of the new optical modules, and then there's also a desire to support 100 gig QSFP28 to SFP28 breakout for 25 gig. Then you say, well, what about 40 gig? Wasn't there this whole thing in the IEEE and all this and that and arguing? And it turns out, yes, there was. We ended up doing 40 gig. But remember, that was the standard was defined in 2010. We were working on the specification in 2008. So technology and the market requirements have changed over those years. So back then, 10 gig signaling was efficient. Now 25 gig signaling is more efficient. So it's kind of evolved in what we can support. The QSFP Plus is also more expensive than the SFP28, and kind of the theme through this presentation is there's a need for both. There's a need for 40 gig, there's a need for 25 gig in the data center. Here's a mathy slide that shows you two different ways how 25 gig signaling is much more efficient. And there's a bunch of there's a number of 3.2 terabit chips that are coming on the market. You've probably heard of Broadcom's Tomahawk. And this fall, and I expect early next year, there's going to be a number of new switches and new line cards in the market. They're going to have 3.2 terabit capacity. So if you look at a theoretical switch, for example, could support 96 25 gig links and 100 gig uplinks, has a full capacity utilization of 3.2 terabits. If we had to do that with 10 gig signaling and using 40 gig, then we would get much less capacity. And the interesting thing is, if you just use an example of a 100,000 server data center network, the number of top-of-rack switches that you need is dramatically less if we use 25 gig. You can also look at different math, which is the table on the bottom. If you use a 10 gig speed, a 25 and 40 and 100, you can see that the 25 and 100 gig based on 25 gig signaling is the most efficient, and that's the one that gives us full utilization of the 3.2 terabit chip. There's two things that are going on in terms of 25 gig. There's the 25G based T study group. They decided just to combine their meetings with the 40G based T task force, so it's going to be one standard for 25 and 40 gig. They just kind of slipped it in there and started meeting together. It's not going to delay the 40G based T standard at all. So that's well underway, expected in March of next year. And then there's also the 802.3 BY Ethernet Task Force, which is working on a couple of different specifications, and these are still being worked on. So this is the information as of 3 weeks ago that was decided in the IEEE meeting. They're working on a couple different things for copper. There's a backplane reach, which is probably not as interesting to you as it is to some of the system vendors. They're also working on some different copper cable reaches, so a 3 meter and a 5 meter. Working on auto negotiation. They're finding some new passive direct attached cables. And they're also working on 25G based SR, which is 25 gig over multi-mode fighter up to 100 meters on OM4. The standard is expected in 2016, and also interfaces expected next year sometime. There's also an industry group called the 25 Gigabit Ethernet Consortium that was founded last year by a few vendors. They're developing 25 and 50 gig standards that are outside of the IEEE. They're working on a 25 gig interface and also a 50 gig interface. The specification on their web page is worded very distinctly and says that they're only going to define backplane and twin-ax copper cable, but does not address or preclude active optic cable or fiber interfaces. So I don't know what that means, and unfortunately the full draft is only available to members, so I can't tell you what's in it, but you can look at their webpage for more information. But I hope that we don't have two competing standards for 25 gig. What I expect this means is that the IEEE will define the copper and multi-mode interfaces, and that there could be a standard for single mode that is done in this group outside the IEEE. Here's a technology reference slide. I have these in at the end of each section for each speed. Typically I don't read them because they're extremely interesting, they're also extremely boring, and they can sometimes put people to sleep, especially small children. The one thing that I do want to mention is that for 25 gig, there's an SFP28. It's just a 28 gig version of the SFP. It's the same size as the SFP and SFP Plus that we use for 1 gig and 10 gig. So you can see that by using the same size optic or the same size pluggable module, you can see that we'll probably have some multi-speed switches that support, gig, 10 gig, 25 gig on the same port, just as we have switches that support 10, 100, 1000 base T today. Okay, on to 40 gig. There's not a whole lot to say about 40 gig. 40 gig is kind of done and in good shape. We have the 40 gig QSFP Plus. We have a number of different pluggable modules. 40 gig is very popular in data centers for breakout. So we have a number of fiber and copper breakout options for 40 gig to 10 gig. We also have longer reach interfaces now for more like aggregation and core applications. The latest development is that we now have a 40-kilometer single-mode interface for 40 gigs. That just came out, that was just standardized in February of this year. So there's not a whole lot going on in terms of development. There's 40G base T, as I mentioned, that's being done jointly with the 25G base T study group. That's expected next year, and then the ER4 interface that I just mentioned was done earlier this year. So we're in good shape as far as 40 gig. As your reference slide. And I'll skip through. Okay, on to 100 gig, and this is where it's interesting and probably worth spending a little more time on this slide. We're finally, if you ever heard of Crossing the Chasm, it's a marketing book that talks about technology adoption, and the cool thing is that one, it applies to anything in the world, and two, as you may remember from your statistics class, it turns out everything's a bell curve at the end of the day. So. Those two things together can describe how the market adopts any new technology, and it has these concepts of innovators, early adopters, early majority, and then that also relates to market volume. So the interesting thing about 100 gig is that I think we're finally crossing this chasm where we're moving from low density, higher cost ports into lower cost, higher density ports. And the two things that are driving that are this 3.2 terabit chip that I mentioned earlier, and also two new optics types, the QSFP28 and the CFP4. Del Oro is a market research group, they project that we're going to ship 1 million 100 gig ports next year. In 2014, the market volume was 17,000 100 gig ports. So you can see that's a pretty big increase in 100 gig ports, and again, driven primarily by the new ASICs and the new optics that we have on the market. And then eventually, in 2018, 2020, whatever, when we have serial 100 gig, then we'll have high density commodity ports like we have today. Some of you have probably seen this slide before, so I'll just talk quickly through it, but it goes back to what I was saying about the first generation of 100 gig technology used 10 gig signaling on the electrical and the optical side. The second generation, we get rid of all the 10 gig and we go straight to 25 gig signaling. That gives us a lot more efficiency and allows us to develop smaller optics modules. In terms of 100 gig development, there's not a lot going on in the IEEE. There's a short reach and SR4 interface that was defined and standardized in February, and then there's a couple things that were removed from the standard, and these are kind of the important ones. There's a 20-meter multi-mode fiber interface that was removed just because there wasn't a point. We have 100 meters, so there wasn't really a big advantage in doing a 20-meter. The one that is important is a short reach single mode interface. There is a proposal to do a 500 meter single mode interface to address hyperscale or large scale data centers where you need to go faster than 10 gig and longer than 100 meters, but there was no no intermediate reach other than 10 kilometers, which was pretty expensive. Unfortunately, in the IEEE, people couldn't come to consensus, so the objectives were removed from the IEEE. Here's just a couple of slides that I'll go through quickly on the module evolution. You can see on the very end we have QSFP28 and CFP4, so this is what's getting us that higher density and also lower power consumption. The QSFP28 in particular is about 3.5 watts versus the original SFP or CFP that was 24 watts. So we see quite a bit of reduction in power requirements and also, of course, much higher density. Here's a couple just other views. I like to show this picture because everyone has an iPhone and you can kind of relate to how big the optics module is, but the original CFP was a very large optic compared to an iPhone 4, and you can see that each generation of CFP and then QSFP 28 reduces that about by half. This is where it gets a little crowded, and if you think of the VHS versus Betamax or some sort of technology choice that we had to face, this is like 4 VHSs and 4 Betamaxes. We had the 10 by 10 MSA, which started in 2010, was very popular early on for two reasons. One, they had a 2-kilometer interface, whereas the IEEE did not have a specification for 2-kilometer on single mode. The second was that the 2 and 10-kilometer CFPs were much cheaper than the IEEE standard. So this was popular early on, but then since we couldn't reach consensus in the IEEE, we have 4 other MSAs that have popped up that are all doing a short reach single mode interface, and 2 of them are even doing a very similar thing using 1310 nanometers 4x25 over single mode fiber. So it's going to be interesting to see how these play out. There's different network operators, different system vendors, different component vendors behind all these MSAs, and basically this is how you can decide with your dollars on which one you would like to support. But clearly the market we can't sustain all 4 of those at the same time. Here's a technology reference slide. And on to 400 gig. This is where it gets really interesting. For 1 gig, 10 gig, even 100 gig, we're basically just blinking a light really fast. For 10 gig, we blink it faster than for 1 gig, but that's basically what it's doing. 400 gig gets really complicated because now we're doing DSP and all these complicated optics modulation schemes because we can't blink the light fast enough, basically. We have to find other ways to increase the speeds. So this is the point where we are in the IEEE, and this is what led us to 400 gig because we know, okay, today Ethernet at terabit speeds, it's not really possible. It's technically impractical and especially economically impractical, meaning if we built it, it would be really large and clunky and you wouldn't want to buy it. We have to balance that with the requirement that we need terabit link speeds soon in core networks. So one way to do that is link aggregation, which is great. The other way to do that is just by providing a faster link speed. So we have to balance all these things. On the technology side, the form factor, optical signaling, electrical signaling, technical feasibility with the market requirements, which can sometimes be vastly different between transit and your internet exchanges, broadband, mobile aggregation, cloud and data centers, content providers. So that's kind of how we have to look at things. The IEEE provides the open forum where we make those decisions, and then it's all balanced by cost. So it all comes down to cost. So that's what we look at when we have new speeds. 400 gig was chosen because it seems to be a good speed that can give us a reasonable increase at a cost that people will actually buy. So that leads us to the IEEE task force. 802.3bs started in March of 2014. They're working on a number of different interfaces, of which only one has been defined. We have 400G base SR16. It starts to be a real mouthful when you have some of these new standards. That's going to be 16 times 25 gigs over parallel multimode fiber. They're working on definitions for a 500 meter, 10 kilometer, and 40 kilometer, 2 kilometer and 10 kilometer interface, as well as some electrical interfaces, a 25 gig and a 50 gig interface. As 40 gig is very popular for breakout, there's a strong desire to support some sort of 4 times 100 breakout from 400 gig. We expect the standard in February of 2017, and also probably first interfaces sometime after that on the market. In terms of Technology considerations, this is where it gets hard, as I mentioned. So there's basically 4 ways that we can go faster. We can just increase the signaling speed. We can change the modulation. We can change the number of fibers that we use or the number of lambdas that we use. And all of these lead us to a lot of different choices. And in the IEEE, this is where the discussion is about all these different encoding schemes and different fibers that we can use. So there's some NRZ and PAM4 encodings with different speeds over different lambdas or parallel fibers in some cases. It looks like, as I said on the previous slide, for the 100-meter multimode interface, that's been decided on. It's going to be 16 lambdas over a parallel fiber. So you'll have a high-density fiber ribbon cable that will be used for 400 gig. For the longer reaches and the single-mode interfaces, it's still less clear. There's a lot of debate in the IEEE about what the right thing to do is and about what the right technology uses. So those things will have to be decided eventually as they build consensus in the IEEE on what the right solution is. In terms of optics modules, there's 2 modules that will be used initially for 400 gig. There's something called the CDFP. This is a 400 gig module that was specifically designed for shorter reach interfaces. And then there's also the CFP2. So you might recognize the CFP2 from 100 gig. Its specification was actually designed to support 100 gig and also 400 gig from the very beginning. So it has 8 times 50 gig electrical inputs that we can use for 400 gig. And then sometime down the road, maybe in 2020 time frame, we'll have some sort of new optical module for 400 gig. It could be some theoretical, maybe a QSFP 100 or CFP4 or something like that, that could actually support 100 gig serial signaling. And this is when Ethernet at terabit speeds actually becomes feasible. So when we have 100 gig electrical and optical signaling, that's when we'll do the next speed increase towards a terabit Ethernet. Okay, so if futures kind of summarizing, Ethernet is continuing to evolve. We have different new speeds for different new markets. The old 10x, 3x, so we used to have this, we want a 10x performance increase for a 3x cost increase. It doesn't work anymore as we get to higher speeds. It was real hard to go from 10 gig to 100 gig. So the old 10 meg, 100 meg, gig, 10 gig, 100 gig, that model doesn't work anymore because the best technical and economic solutions are somewhere between 4x to 8x the lane speed. So we have 4 times 10 gig for 40 gig, we have 4 times 25 for 100 gig, 8 times 50 for 400 gig, and then based when it happens with the higher speed electrical signaling, we could see some new Ethernet standards around 50 gig signaling. In terms of the speed evolution summary, summarizes everything that we talked about. 2.5 gig and 5 gig are coming soon, in particular for higher speed wireless access points over legacy cabling, Cat5e and Cat6. 10 gig is widely deployed everywhere. 25 gig is coming soon for server and top of rack server applications. As I mentioned, the math just works out really well to fill those 3.2 terabit chips. 40 gig is still increasingly deployed in data center networks, again for the 4x10 breakout that I mentioned. For 100 gig, we're really in the second generation with the 25 gig signaling. We have new optics technology with CFP2, but also in particular with the CFP4 and QSFP28 that will be shipping later on this year. Some people are shipping it already. We're still ways away from 100 gig serial signaling, but we'll get there eventually. 400 gig development is well underway and based on 100 gig technology. Ethernet at terabit speeds. You notice I don't say terabit Ethernet, I say Ethernet at terabit speeds because it's likely that the next speed increase could be 1.6 terabit. It's unlikely that we'll see a 1 terabit speed exactly. So that's still unfeasible right now. Again, for the tech and the economic reasons, it's just not feasible to make it. But we'll get there eventually, sometime around 2020 plus when we have 100 gig serial signaling. I have a ton of reference slides. Here's more information. The best way for you as network operators to get involved is to get involved with the IEEE. Here's all the task forces and study groups that are going on right now. You can also look at all the optics MSAs. They're interesting to read the specifications, and they're all freely available. So it makes good reading in your spare time. And after this, there are tons and tons more reference slides, but we don't have time to go through them all. So that's what's going on with Ethernet. Any questions?
Hi, Chris Williams with Twitter.
Yeah. Hey, Chris.
Hi. So just out of curiosity, at what speeds do you think we're going to start having problems getting those speed levels out of the glass that's currently buried underground today and start running into the speed limits of the current way that fiber is laid? You know, inside a data center, you can always run different fiber.
Yeah.
Backbone, not so much.
That's a good question, and I don't know that. I'm not an optical expert, but I can tell you that there is a huge deployment of, I forgot the single mode specification, it's G709 or something. There's a huge deployment of that fiber everywhere in the world, so that's kind of the common denominator. So all of the current developments are expected to run over that single mode fiber. I mean, it's possible based on, the different modulation schemes that you may need some specialized fiber, but I don't know enough about it to answer that. I'm sorry.
Okay.
Good question, though. Okay. See, Kevin
Bloomberg, The Wire. So I can get from my closet, my server closet, to my bathroom really easy with these standards. But I was looking at all the data, and it's great. I'll read that on the plane. But I didn't see anything long reach, like really long reach. So is the internet shrinking? Is the world shrinking? Or is this a real missing feature?
No, it is not, and that's a great question. So you'll notice the IEEE has defined interfaces up to 40 kilometers. Some of them, for example, there's an 80 kilometer or even 100 kilometer 10 gig. It's not really an IEEE standard. They just increase the power. But the problem is as you get into these longer ranges, that's when it gets into optical companies' secret sauce, and that's where everyone, like the Infineras and the Sienas, and we have an optical platform. That's where it's all patented, very proprietary technology that allows you to go those far distances, and there's not going to be any standardization around that.
Thank you.
Good question.
Is there any new technology or algorithms working at layer 1 for new CRCs or FEC or MACsec?
The IEEE is not addressing MACsec in these standards, but yes, FEC, or the forward error correction FEC, is included in many of the new standards. The 25 gig standard in particular has a no FEC, an RS FEC, or the 100 GKR FEC option for different distances. The 400 gig standard is being written so that the architecture includes an optional building block for FEC, so it's not kind of an add-on as it has been for some of the different 100 gig interfaces. So yes, it's a consideration.
And will the CRCs need to be stronger because of higher speeds and longer distances or anything, or they're not changing anything there?
No.
No.
No. Okay. Phil, and then, okay, last question from Phil.
Phil Rosenthal from IS Prime. So there's been some other discussions in the past about MTU increasing and being a controversial thing, and we're kind of stuck with 1500 being the standard. But that said, any chance that we might be able to get an auto negotiation where if I configure one side as 1500 and another side as 9000, that they'll say, hey, this is a mismatch, and pick this, the smaller number that'll actually work?
Yeah, so good question. This probably comes up almost every time I give this presentation, and I'm sorry that I never have a good answer for you, but and this came up at RIPE too, when Martin and Rudiker had a discussion about it. There's no interest in the IEEE on defining some sort of maximum frame size. In fact, all the standards, the first line is almost always preserve the existing frame format. So there's a lot of interest in the IEEE on maintaining compatibility with the, millions or billions of Ethernet devices that are out there. And it would be very difficult, I think, to have some sort of auto negotiation thing for a larger MTU size. But this is where, if this is important to you, this is what I say all the time, and I don't think it's a very good answer, but it's the only answer that I have, is if jumbo frame standardization is important to you, then you need to be talking to your system vendors about it and make them do something about it in the IEEE. Because without a large demand from you, the customers, and the network operators, no one's interested in doing it in the IEEE right now.
All right, thank you.
And I'm sorry that's not a very good answer. Okay, thank you.
Thanks,